Hi everyone, our project is Vismood, which is emotion-aware image-to-text generation. In the motivation part, the current models can generate emotional captions, but they are not quite predictable and controllable. So our goal is simple. Given an image and a target emotion, generate captions in that style. It's not emotion classification. We just provide the model with an emotion, like set here, and it learns to write captions in that tone, even if the image itself doesn't look sad. To train our model, we use around 30K image caption and emotion tuples from two datasets. RTMs gives us a highly quality human emotion annotations. And for Flickr AK, we generate labels using the robotic classifier and we manually check them for the basic correctness so we can use them safely. Each training input includes an image and a prime asking for the captions in that in our target emotion and also emotion label.
Our architecture is shown here. The image is encoded by the vision tower and its features together with the prompt and target emotion enter the language decoder. We insert MVEA models into selected decoder layers so the emotion signal can directly shape higher level semantics rather than stay as a surface prompt. During training, both the vision encoder and the language backbone stay frozen. Only MVEA and the emotion projection layers are updated. The emotion condition output is then compared with the ground truth caption to compute the joint loss. This is the internal structure of MVEA, which contains two complementary emotion control paths. On the left is the adapter-based path. The hidden state goes through a down projection, an emotion control gate, and an up projection, allowing the model to modulate the magnitude of the hidden state. On the right is the emotion LoRa path, where the emotion embedding generates a low-rank direction that adjusts the direction of the hidden state.
In the training part, our base model is a Lava 5.3 minute, adding the MVEA and also visual encoder and language weapon to speed up the training and keep the model stable. We jointly optimize three losses. Caption losses keeps the captions correct. Emotion constancy loss enforce the specific emotional tone. The clear score ensures the captions stay aligned with the visual content. To evaluate our model, we combine emotionally related with a language quality matrix. For emotion accuracy, we simply feed the caption into robotic classifier and see if the predicted label matches the target emotion. For the emotion score, instead of using classifier's final label, we compare its probability distribution to the target emotion. The clear score evaluates alignment between the caption and the image. So for the language quality, the PBL for the fluency, the distant N for the lexical diversity, and also the human evaluation are around 20 participants surveys. Weights for emotion and the image relevance.
Here are our experimental results. As you can see, the improvements in emotional performance are very clear. Emotion accuracy, distinct to, and human emotion relevance are raised substantially above the original Lava Mini model. And the overall performance approaches that of GPT-4o. At the same time, there's a mild visual consistency trade-off. After adding MVEA, the clip score drops slightly. Finally, the language quality remains stable. We also ran ablation studies to examine the role of each component. The blue curve, representing the full model, remains the broadest and the most balanced across all metrics. The orange and green curves, removing gating and removing the LoRa path, shrink noticeably on emotion-related metrics and human scores. The red curve, corresponding to removing emotion embedding, drops the most because the effective signal is essentially cut off at the source. Overall, gating and the emotion embedding provide the largest gains, with the LoRa path adding smaller auxiliary improvements. We also conducted a position ablation, inserting MVEA deeper into the decode yields stronger emotional control, with the highest emotion accuracy and human-rated emotional relevance, likely because deeper layers are closer to the final generation decisions. Here are our qualitative results. On the right, it's not good. The target emotion calm was not obviously reflected, and the caption stayed neutral. On the left is a success case where the model captured both the scene and the calm tone. These examples show where emotional alignment works and where it breaks.
So our results make sense. MVEA constantly improves the emotional control, and ablations confirm each component matters. The improvements were stronger than expected. The click alignment drops more. If we do this again, we will start with more research to turn the loss rate and the module setting more carefully. Our main limitations are testing MVEA only on one backbone and still having our emotion vision trade-off. Next, we plan to try larger models, run deeper ablation, and decrease the emotion vision trade-off. Thank you for listening.